By the way, all these formulas that we're going to do, I'm going to do these after I finish these PowerPoints. Okay, so I'll just talk about the formulas for right now. This formula right here, we're not actually going to use it like plugging in uh, a great deal of numbers. What we're going to do is we're going to compare some situation like this to another situation where you take the exact same two objects, the same masses, but you spread them apart more, or you bring them closer together. All right, so you'll see. We'll do some examples like that. So big G is called the universal gravitational constant. It has a value. There's the units. Don't worry about the units too much. The value is 6.67 times 10 to the minus 11th. All right, so that's the value of big G. It was measured by a guy named Cavendish. So this is a full, um, this is a full lifetime after Isaac Newton. Um, and just to let you know, so the Cavendish was a very famous British physicist, and in fact the laboratories that he worked on, or where he worked, were are actually still there in London. They're called the Cavendish Labs. Just to let 100 years after this, almost exactly 100 years, so around 1898, there's another person working in the Cavendish Labs. Now he's not interested in gravity or anything like that, but this fella, who's working in 1898, or right around there, he's working with this new thing called a cathode ray tube. Um, and the cathode ray tube, he was actually the first one to determine that there were these little negatively charged particles called electrons. So in the Cavendish Labs, again, 100 years after this guy J.J. Thomson comes up with the one of the fundamental discoveries of the electron. Um, all right, so in this formula is this is for what's called centripetal acceleration, when something's going around in a circle. What's important is what we're going to equate that with Newton's law of universal gravitation. Right now, the actual deriving the formula, which is the next slide, that's what this is all about. This is deriving the formula. The first thing that they get here is the formula for um, the orbital velocity. All right, a little bit later we'll come to the formula for the escape velocity, and then this equation right here. This is not it's not normally used this way, but this is an equation called the modified version of Kepler's third law. But if you put in what the velocity is, you get this formula. This is really the true modified version of Kepler's third law that is used all the time. All right, so this basically remember with Kepler's third law, which is, he doesn't know what the mass of the sun is or anything like the Kepler didn't anyway. And uh, he realized that a cubed, which was the semi-major axis, equals p squared, which is the period in years. So a has to be in units of astronomical units, whereas this thing, any two objects in the universe that are in orbit around each other, or if one object is orbiting another, you can use this formula to get, if you know how far apart they are and what the period is, right? These are things you measure. You can figure out the mass. All right, so that's called the modified version of Kepler's third law. And as I said, so if you include a square root of a 2 in here, that's called the escape velocity. All right, so the derivation of these is not important. What's important is that d has to be in meters, the period has to be in seconds, and the mass has to be in kilograms. Right, so that's what's important about that. All right. The next formula that we're going to see is deals with what's called surface gravity. The surface gravity of something is, how fast it if you drop something, how fast it accelerates is called the surface gravity. On the Earth, that value was well known. It's 9.8 meters per second squared. In fact, Galileo himself is the one that was first measured this. And not only that, he measured this without having a clock. They didn't even have clocks back then that could measure seconds. So it's pretty remarkable that he was able to do this. This is I like in the formula sheet for test one. This is called A sub g, right? So this is the acceleration due to gravity. There's big G again, the 6.67 times 10 to the minus 11th. M is the mass. So if you put the mass of the Earth in here, and if you put the radius of the Earth in here in meters, the mass has to be in kilograms. The radius of the Earth in meters, and you square that, you get this 9.8. All right. So like I said before, on the moon, it's the acceleration due to gravity is about 1/6. 1/6. You divide it by 6. So remember, the mass doesn't change. It's the weight that changes. All right. So that's a big deal. All right, and then we come to escape velocity. All right, and so let's see, where's the equation? There it is, right there. So there's the escape velocity from. And by the way, when you do this formula, v comes out in meters per second. A big, so that's 2 times 6.67 times 10 to the minus 11th. That's big G. The mass has to be in kilograms. R has to be in meters. It's often given to us in kilometers. And so this answer, the escape velocity, just like the orbital speed, comes out to be meters per second. And then if you divide that by, very often you'll see tables where you're given escape velocities. So for example, there's the Earth, it's about 11.2 kilometers per second. So it's like, 11,200 and something. We'll do an example with that. I will use the Earth as an example. All right, and so remember, that's the escape velocity it's tremendous, right? Just to give you a sense, and I don't normally, we normally do things in standard international units, but just to give you a sense, the orbital speed, right? The speed, where's that? Oh, let me look at this slide. This one back here, where the cannon is going all the way around the Earth. I should have. So, there, this one. So the orbital speed, all right. The speed which something has to travel to orbit the Earth and not get any closer to the Earth, like these trajectories, but go all the way around the Earth, is about 17,000 miles per hour, right? 17,000 miles per hour. All right, now you put that square root of 2 in there, and you're at the escape velocity, right? So so that's this formula right here, and then to escape the Earth, it requires. Okay, so this is in kilometers per second, but just to give you a comparison, this is roughly 25,000 miles per hour. That's how fast you have to go to leave the Earth and never come back. All right, so remember the International Space Station, satellites that are orbiting the Earth, they're all traveling at about 17,000 miles per hour. If we were to go to the moon, which of course we already did that, hopefully we'll do that again in the near future. If we go to Mars or anything like that, we have to reach 25,000 miles per hour. All right, so that's when you compare these, that's about what the speed is. All right, so yeah. All right, so that's the escape velocity. Once something reaches escape velocity, it leaves the Earth and will never ever come back. All right, I'm going to do some examples. Probably in the next video, I'll work out some examples.